session. We're including a lot of things in this session, a lot of things that need to be included in the UFS for us to best understand our Earth processes and those phenomena that happen that impact us right where we live, especially if you live on the coast. Our first speaker is going to be Ayumi Fujisaki, and she will be virtual and sharing her screen. And I think that she is all set up and ready to go. So as soon as we're ready in the back, I can't talk any slower, guys. We're ready? All right, we're ready. Take it away, Ayumi.
Thank you, Tracy. I assume everybody can hear me okay, but yeah, just let me know if I seem quiet. Hi, everybody. I'm Ayumi Fujisaki Manome from SIGRA at the University of Michigan. I will be talking about NOAA Unified Forecast System Coastal Applications Team, or UFS-CAT, model evaluation. I'm really speaking on behalf of a very diverse team, including both federal and academic partners. Several of the team members have presentations this week. Saeed Moghimi led an awesome panel yesterday on UFS Coastal, and also Saeed Memari will have another talk later in this session too. And we wanted to take a moment to sincerely thank NOAA NOS Water team for their funding support, and also Dr. Chanshen Chen, the developer of FECOM, and Dr. Joseph Zhang, the developer of Schism, and he's gonna give a talk later in this session too. They both provided really valuable support and advice to the testers on model configuration, troubleshooting, etc. throughout the model evaluation. And finally, we wanted to thank Texas Advanced Computing Center, or TAC, for their support for providing computational resources. Background, UFS-CAT is part of a larger development within NOAA that include federal and academic partners to review NOAA needs and consolidate them into individual modeling systems, using a smaller set of coupled Earth system models that would continue to serve its various stakeholders. There are 3 sub-applications: marine navigation, risk reduction, and total water level. In phase 1 effort, the team requested all 3 sub-application teams to generate consensus guidelines for further model evaluation. That include metrics, criteria, and competing numerical oceanographic models. The consensus guidelines have been documented into 3 NOAA tech report for all of the sub-application teams. So yeah, if you're interested, check them out. We are currently in phase 2, which is about actual model evaluation. The team decided to further pursue marine navigation sub-application for this phase 2 model evaluation. Based on phase 1 outcomes, 2 ocean models were selected, FECOM and Schism. They are both unstructured mesh hydrodynamic models. And then in this phase 2, we have had 9 tester groups, both from academia and government. And we designated 2 hindcast period. Both of them have multiple hurricane or nor'easter event, and therefore ideal for model evaluation. This phase 2 consists of 4 rounds. Round 1 was fairly simple, evaluation in 2D tide only mode. 2D means depth averaged, and then only tidal component were evaluated. And then in round 2, we expanded it to 3D mode, and then models were forced by atmospheric model output. And then round 3, it was same as round 2, but we included wave processes based on Waveboat 3, and we also started using UFS coastal infrastructure. We are currently in round 4, and round 4 is the same as round 3, but we further included national water model output as a river forcing. This is a study site, New York Harbor. each tester generated their own mesh. And then on the left, you can see map of bathymetric data set. Number on top of each polygon represent horizontal resolution of each bathymetric data set. And then on the right, you can find example mesh developed by testers. The top one is schism mesh example, and then bottom one is FECON mesh example. Because this model evaluation effort is not really about bake-off, but it's more about advancing readiness level of these two ocean models, and then about understanding from the processes. We are not really showing any specific results, but wanted to focus on outcomes. One outcome is training the next generation coastal ocean modelers. A big success is graduate student test. We have had total 9 postdocs and grad student, and also the advisors. They are all exposed to coastal circulation models used by NOS, NOAA's operational and marine navigation user requirement, NOS model development and implementation approach, and various observational platforms and skill assessment approaches. There are also lessons learned. Sustained collaboration and regular communications have been very important to keep the team going. Each tester had their own baseline as a starting point, and this allowed flexibility in learning by a trial and error method. All information in NOS National Bathymetric Source should be used, not just depth data, but also source and uncertainty information should be used. There are also challenges. Baseline approach worked pretty well, but it also made it difficult for a tester to discuss their particular model issues and obtain troubleshooting help from other testers. We encouraged testers to follow guidelines, share knowledge, lessons learned among the testers, sort of forming a mutual learning network, while still providing flexibility and trial and error learning approach. Another outcome is evaluation of potential coastal ocean models. Successes include performance assessed for the two ocean models as a potential candidate for coastal ocean model component of the UFS. Testers evaluated the ability of the two models to predict the conditions according to NOS standards for the both hindcast period. Lessons learned, there's a need identified to balance the requirement to generate accurate high-resolution hindcast versus practical computational constraints, such as NOAA's operational HPC environment. Importantly, advanced testers were able to contribute code to the UFS coastal coupled infrastructure by expanding the number of atmospheric variables in coupling, and also merging code into the UFS coastal Git repository. There was a need for NOS to continue its development of open source skill assessment software, not just for surface, but also for subsurface and spatially. There's also a need for local knowledge to understand model observation differences and also digitized bathymetry versus bathymetry collected by an acoustic system. So this is an example for the need for local knowledge. On the left, you can find a map of our channel. This is Arthur Kier area. One tester, Said Memari, identified inconsistency across different bathymetric tiles. There was an error with it, and that was fixed. But we also found additional suspicious jumps in bathymetric data. But based on the input from a local expert from weather service, those jumps are actually deemed as real. So we decided not to touch them. On the right, you can find another example identified by Kyumin Park, another tester. Now you can see a broken lever on the left. There was an issue with old digitized bathymetry. One of the co-lead fixed this using the latest bathymetric source, and you can see a fixed map on the right. So local knowledge of physical oceanography and bathymetry are very critical in properly configuring and evaluating the forcing used by the two models. Okay, summary and next steps. We are currently in round 4, which will run through the end of this month. Evaluations so far indicate both models are viable candidate to be a coastal ocean model component of the UFS to support marine navigation application. The team has trained next generation ocean modelers, 9 postdocs and students, 2 peer-reviewed publications, 10 conference presentations so far. We also have 2 NOAA tech report published from phase 2 and 1 more in prep. We also have an overview manuscript in preparation for submission to BAMS. This is led by John Kerry. And finally, I wanted to conclude by expressing sincere thank you to all the partners for making this report a success. That's it. Thank you.
All right, we have time for one question.
Yes. So, yeah, any questions? We're almost at 7 minutes, so if there isn't, yeah.
Okay.
Isn't
All
it-
right.
Yeah.
We can move on. Think about that. This project is super awesome. This is the one of the projects that while I was at NOS I was most proud of because it took what the UFS wants to do and actually applied it, getting the community to use our code, trained on our code, and it grew our community substantially over the past 4 years. All right. Next up is Joseph Nisley. I was gonna make the K silent. Okay, thank you.
Hi everyone, my name is Joey Nisley. I am a graduate candidate at the University of Maryland and also a Wings Fellow, and today I'm going to be talking about obstacles for high-resolution HAVs over the entire Atlantic Basin. All right, so we've seen lots of presentations about HAVs this week. We know that it performs well, but some issues are that it relies heavily on the GFS and it features rather limited DEA over a small nest, and this constrains capabilities. We operate HAVs with a static basin-wide analysis domain with uninterrupted assimilation of measurements domain-wide. And such a configuration allows us to explore a variety of DA methodologies that we otherwise might not have been able to. High-res ensemble DA and forecast, online radiance bias correction, and so on and so forth. That being said, model physics parameters are very carefully tuned to the TC application, and they may struggle to characterize broader environmental conditions. And so expanding this analysis domain size while maintaining this high resolution convective allowing resolution requires very careful consideration of the model physics. So our goals, like I said, we're operating HAVs with a static high-res analysis and forecast domain. If you look over at the big pink basin-wide analysis and forecast domain, this is what we're talking about. We're doing continuous domain-wide DA, and we're using ensemble methodologies to produce probabilistic analyses, from which we initialize an ensemble of storm-centric forecasts which resemble the operational domain. And in this case, what I'm talking about is the purple domain there. It's storm-centric 6 kilometers with the inner purple box, which is the moving 2-kilometer high-resolution nest. And we're going to explore and compare 2 analysis domain configurations, 3 and 6 kilometers. And we're going to look at how these high-resolution ensembles, high-resolution initial conditions and ensemble data can affect TC forecasts. And we're going to explore the potential deficiencies with just expanding this domain over the whole basin. But we're also going to highlight the potential for probabilistic TC forecasting and all the benefits that come with that. And so very quickly, some details about the model before I jump into results. We're using a 3D ENVAR analysis. We're getting our flow-dependent error covariances with a 40-member HAVs ensemble, which is high resolution. It's 6 kilometers. We're also doing an online radiance bias correction, and so that means that the bias model for the clear sky radiances is trained on the native modeling grid. And as I said earlier, we have this basin-wide analysis, and it provides the initial conditions for these 10 these long storm-centric forecasts, which you can see off to the right, the progression of this 10-member forecast ensemble over the life cycle of Earl. We're using the HAVS-B physics scheme. Now this is a slightly older version of HAVS. This is HAVS V1. I know that they have made some improvements. They changed the ocean model entirely, and they made some improvements to the physics and to the model resolution, but I believe that these results are absolutely still applicable. And we're covering a 20-day period with 2 named storms. Now I'm going to jump right into results, and I'm actually going to skip that slide. The very first thing that we noticed is that these changes in forecast resolution, they're resulting in some pretty notable differences in the placement and concentration of cloud fraction and specific humidity. If you look at our figures, we have on the top cloud fraction, on the bottom specific humidity, 3, 6 kilometers, and then the difference here, red means that the 3 kilometers is higher, blue means that the 6 kilometer values are higher. And so we're noticing immediately, we're seeing a lot more humidity in the form of like nimbostratus clouds around 700 millibars in the 3 kilometer configuration. Conversely, with the 6 kilometer configuration, we're seeing changes in static stability, which lead to more humidity in cumulonimbus clouds throughout the mid-troposphere. I also want to point out the higher cloud fraction at higher altitudes in the 3 kilometer. This is a cold cloud bias. This is also an interesting result. And these changes in cloud coverage and specific humidity, we wanted to see next how they affected surface variables. And so in particular, we're going to look at now downward shortwave radiation flux at the surface. Now this is a diff plot, again. Positive values here means that the 3 kilometer configuration has higher values and vice versa for negative values. We split it up land, ocean, total. And you'll notice immediately that all of these values are negative. The 3 kilometer results are resulting in significantly less downward shortwave radiation flux. And I do mean significantly. Some of these watts per meter square values are, pretty big. And so we can also take a look at downward long wave radiative flux. These values, you'll notice the y-axis is an order of magnitude smaller. And so these are less significant overall, but I do find it very interesting that when Earl and Danielle are both very active, we can see that in this figure. I mean, we can see that the downward long wave radiation flux changes relatively over the ocean. And next, we want to look at how this affects surface temperatures. And so I'm actually just going to skip this slide and show one slide which compares all 3 of the figures I just showed you. You can see that the temperature difference at the surface is down at the bottom. Again, these are the diff plots, same format. And you can see that clearly these changes in downward shortwave rad flux is resulting in differences in the temperature at the surface. And the next question is, okay, well, that's just the surface, that's just the temperature of the surface. How does that affect the whole atmospheric column? And so for that, we're going to take a look at a domain-wide and time average O-B verification of the forecast. We have temperature off to the left, RMSE and bias, relative humidity off to the right, again, RMSE and bias. Don't have time to dig into all of this, but I do want to highlight a few key items, namely the kind of strong and negative temperature bias for the 3 kilometer at the surface, the strong positive temperature bias aloft, and also you'll notice a dry bias in the relative humidity at the surface. And 1 minute. Oh, okay. Are there 7-minute talk? Okay, I thought I had 10 minutes. So this is obviously going to affect static stability quite a bit. We can see that manifest very quickly in the presence of different types of precipitation. We can see that the 3 kilometer has much more non-convective precipitation, and vice versa for the 6 kilometer. The Cape is much greater for 6 kilometer. I'll just run through these results real quick. I won't be able to describe these results, unfortunately, but I just want to highlight that a few things. First of all, there are noticeable differences in TC-specific aerometrics. And intensity results are a little bit more mixed, but I want to highlight the utility of using an ensemble forecast here. You'll notice these metrics are much less noisy than maybe a deterministic forecast. And we can also examine things like the spread and how dispersed that is. In this case, very underdispersed, unfortunately, but we do have a follow-up study that is looking to address some of that. All right, and so halves can benefit from the self-contained basin-wide analysis configuration. Differences in cloud coverage and composition are resulting in significant air mass biases, and altogether these results should help us inform how we design and tune future halves model configurations, especially basin-wide configurations and ensemble DA configurations. Thank you.
Can you hear me?
Yeah.
Okay. Have you tied this to any specific physical parameterization, like a convection scheme?
I'm sorry, can you ask that again?
Have you tied these differences at different resolution to a specific physical parameterization scheme, like the convection scheme?
Yeah, I mean, we've been looking at we're using Thomson microphysics, and so I'm comparing my results to other papers that have focused on this subject, and I'm seeing a lot of similarities, and so, but there's a lot of work to be done. I think it could also have something to do with the FE3 dicore and how that behaves at high resolutions. But yeah, we are attempting to do that now. It would have been nice if we could have run some like physics sensitivity tests, but these are unfortunately very expensive experiments.
But do you have a deep convection scheme in this halves B setup?
Oh yeah, it's the scale-aware SAS scheme that it's the default halves B physics scheme.
I mean, my guess would be to start there actually, but
Okay.
just a
yeah.
guess.
Yeah. Okay. I'll definitely look at that. Thank you.
Yeah, thank you, Joseph.
Yeah. Thanks.
Yeah, and just repeat it again. It's 7 minutes talk, but if 7 minutes is kind of finished the talk, then maybe we have time for 1 or 2 questions because we packed and try to give more opportunity to more number of people. So that's why we want to stay very economic with the time. Thanks.
All right, and I just wanted to introduce Joseph. Raise your hand again. Ed, will you raise your hand? Ed Myers. Okay, and Saeed. Please all meet each other. Joseph is graduating in December, and he is an expert in DA. I'm sure Alex would love to have him. All right, next up is Kristen Barton.
Hello, everybody. So I am Kristen Barton. I work at NOAA, and I want to talk about some of the work that NOAA PSL has been doing on trying to put together a Arctic regional coupled application for the UFS. All right, so I just want to give first just highlight the main goal of this project, which I sort of just said, but it is to add an application to the UFS. So we're not quite there at this point, but I'll talk about some of the progress that we've made on at least putting together this configuration and sort of what we hope to see in the future. So we have what's called the Coupled Arctic Forecast System, CAFS, already that is being run. But this is not part of the UFS, and it uses different models. So we would really like to have this Arctic forecasting capability within the UFS that can also help sort of align the research goals and any research we do. Improving the model, of course, can be fed back into UFS. So it will be used, as I said, sort of alongside observations and whatnot to improve the physics and everything. So right now, we've focused on including atmosphere, ocean, ice, and land in the model. We don't have waves. That's something we're hoping to do, but I'll give a little bit of the output and show you what we have, and working on 10-day forecasts. Eventually, we do want to perform sort of concurrent and retrospective runs and a mix there. So to dive a bit more into the configuration details, as I said, the focus right now is sort of kind of the big three of the atmosphere, ice, and ocean to get the Arctic, really look at the Arctic. There was also actually, so we've had to work on a fork. There's a slight change to, we've had to add a Arctic coupling mode specific to the Arctic to get this working in this regional setup that we have. So that's not on UFS right now, but it's something we've been working on. And as I mentioned, we have sort of a test case, a 10-day test case that's running. A big part of this was also setting up the initial conditions, so not just the configuration of UFS, but also we're working with the GEFS v13 replay data sets right now and using that as sort of, it includes all the different components that we're using. So we have it feeding into the ice, the atmosphere, and the ocean for both lateral boundary conditions and initial conditions. And right now the setup's a little bit where you do the, you run this workflow a bit separately, and then you have sort of your run directory, and you can add these initial conditions and lateral boundary conditions into your run directory. But as I said, we want to sort of unify things into UFS a bit more as we go. And a little bit on the grid domains that we're working with. So check the time. So right now we're working with the ocean and the ice share a grid, which is 10-kilometer horizontal resolution and 55 vertical levels. And one of the key things we wanted to do when we focused on this was make sure there's no ice at the boundaries, since that will make things a little bit difficult. So we're trying to focus on a large enough grid that we can get the whole Arctic in there without worrying about those ice boundary conditions. And then at the bottom, you can see comparing the ocean to the atmosphere. So the atmosphere is a little bit larger than the ocean grid. Right now, it's 50-kilometer resolution. We do want to refine that further moving forward, but for this test case, this is what we're working with. And then 127 vertical levels. So one thing just real quick, and I won't go into the details too much, but I have some comparison between the UFS Arctic that we're working on and the CAFS model that is currently running. So of course, one of the big differences is that we're using the same component models that are in UFS. So we're using MOM6, whereas it had the POP2. We're using SICE6, and it had SICE5. In general, for the ocean and the ice, it's actually not that different. The resolution is the same. And I'll go to the atmosphere. So the atmosphere in ours is much more coarse, but as I said, we are looking to refine that further. And then another thing I just want to point out is that we're using the GFS v17 physics suite as well for our atmosphere run. So I did include a very quick comparison to HAFS as well for the ocean. This is some information I found on the HAFS v2.1. Which I won't go too much into detail, but I think HAFS is the only other, when I was looking for other applications that use a regional MOM6 setup as well, it's kind of interesting to compare their sort of regional MOM6 to ours. And then there's also, I wanted to discuss, again, we're sort of exploring potential, how we want this application to be set up. So another possibility is we've been looking at this much more higher resolution ocean grid from HICOM that is 1.8 to 2.4 kilometer resolution. So we'd be able to get, sort of refine it further in that way. And then just some quick output. So right now we have this configuration working. We haven't gotten to the point of doing a lot of analysis or tuning on the model, but we have this 10-day forecast that I mentioned running with. This is just showing some quick output of the 2-meter temperature, the sea surface temperature, and the ice concentration over this 10-day forecast period. And then a very important part of this isn't just the configuration, but of course developing some of the physics and trying to improve what we're doing in the Arctic. So there's 3 important key parameterization improvements that we've been focusing on that of course will improve the Arctic configuration, but also will through this be able to feed back into UFS. So one is the stratocumulus mixing scheme. So we found that there are some issues with simulating this in the models right now, and there's been some work done to sort of put together a new scheme for this. It's been tested on a telescoping nests from 25 kilometers to 5 meters. That's not in our configuration, but it's a scheme that we've been testing and comparing to the TKE EDMF scheme and showing the improvements that we get from this new scheme. Also, some effort to put PUMIS, the parameterization of unified microphysics across scales. This is a cloud microphysics scheme that can simulate the mixed phase clouds, and so there's work adding this into the CCPP suite so that it's accessible to everyone. And then also work on the ice melt ponds. So there, some comparisons to mosaic observations have shown that the SICE isn't quite getting these melt ponds correct. And so there has been some work on improving that and sort of trying to get that merged in, which again, there's still some work to do on evaluating some of these effects. But overall, this is just sort of a look at the parameterizations that we can hopefully use to improve both the Arctic and then all of UFS. So the future goals, so as I mentioned, we have this output that we've managed to get together. We need to work more on sort of the validation, refining it, and then feeding these developments sort of back into the UFS weather model code base. And also, you know, adding some of these new components as well. As I mentioned, there's no waves in it right now. It would be interesting to look at what else we can do. So I included my contact information here. This, as I said, it's still in development, and I would be very interested to get feedback on people who would be interested in using this or collaborating on what, you know, moving forward, what the community really feels would be the best direction to go with this project if there's feedback and whatnot. So thank you.
We have time for one quick question. Go ahead.
So I really appreciate the effort that you've been doing for quite a while in taking an existing model and do the effort to bring it into a community effort stuff. So kudos for that one. But in that context, how do you see this model? Do you see this as a research model, or do you see this as something that should find some kind of way into operations at some point?
So I think right now, a lot of the focus has been on the research of improving the parameterizations. But I know that CAFS is used right now, the existing one is being used a sort of, it is running forecasts right now that are being used. And so something like that, and I do think ultimately if there's a way to get it into operations or if there's a use case for that. Okay, yeah, I think this would be, yeah, good to talk about.
Thanks a lot.
All right, thank you. Round of applause for Kristen. All right, next up we have Scott Dursky. Oh, wow, I've never met you in person. Oh, it's so nice to meet you. You're like a legend.
A legend? Okay.
Yeah.
Well, that puts the pressure on me now. Okay, thank you to the organizers for the opportunity to talk today. Thank you to NOAA and NOS for the continued federal funding. I'm from Oregon State University, and I'm going to talk about a collaboration that we have with NOAA, NOS, SDOF's team for UFS Coastal. I should squat down a bit. Okay, thank you. So a lot of the work I'm going to talk about today is primarily that of Joey Smith, a research associate at Oregon State University, but it has benefited greatly from everyone on this list, along with Ed Myers, who I didn't get to add to the list before I submitted this slide. So STOFS 3D Alaska is a planned operational forecast system that NOAA is building that hopes to incorporate both WaveWatch 3, an ocean model, and an ice model. Other components of the STOFS for the Pacific and Atlantic couple the ocean and the ice, the ocean and the waves, but this new piece that's required for Alaska is the ice component. The domain we hope to cover is all the way from the southern fjords to Point Barrow in the north, and all the way to the west to the Koryak and Kamchatka coasts. It skipped, didn't it? How do I backspace? This one? Okay. So this is a NOAA crowd, and you probably don't need as much motivation, being that you guys are more attuned to the operational end user needs than academia tends to be. But I'll include this slide anyway. For the Bering Sea, there is a significant need for navigation and for storm surge forecast that doesn't exist presently in a 3D forecast model. The Bering Sea has one of the most productive and profitable fisheries in the United States. Shipping, there is a significant shipping route that goes between Unimak Pass and the Western Bering Sea that contributes to shipping cargo and oil between Asia and North America. There are also significant weather events that happen in the Bering Sea. As I demonstrate here, in September of 2022, the typhoon Merbok made a bit of a left turn and turned up into the Bering Sea, creating very high sea states and flooding in areas like Gamble, Alaska. I think when you look at the world map of wave heights for those few days, they had the highest wave heights anywhere in the world during that time. And so we have some coupled barotropic wave models and things for the Bering Sea, but we're at the point computationally where we could really invest in a 3D coupled model and the refinements that a 3D coupled ocean model provides to an environment like this. And you really need a 3D fully coupled model to accurately get the ice evolution with thermodynamics in particular. So the model for sea ice in UFS is SICE, and SICE was developed as a climate model. So there's some question whether a model like SICE can be appropriate for the spatial and temporal scales that you find that you need for an ocean forecast on these scales that we're interested in. And so one of the main things that is missing from SICE historically is open boundary conditions. It's normally used in polar contexts. You just set your boundaries far enough away. You never have to worry about inflowing or outflowing ice. So one of the things that we helped contribute to was implementing open boundary conditions in the version of SICE that's in UFS Coastal. There are other issues that you need to worry about with a sea ice model at these scales, issues of linear kinematic features, issues of resolving thermodynamic processes with the thermodynamics that's in SICE. But there's already been significant evidence to suggest that SICE will perform well in the Bering Sea. Ayumi, who spoke first in this session, has done some work in using a standalone SICE in the Bering and Chukchi Seas and demonstrated that it does perform well in capturing important features like the evolution and persistence of landfast ice along the Bering Sea and Chukchi coasts, Bering Sea and Chukchi coasts. So I'm going to talk about where we started. We started with a standalone ice model within UFS for the Bering Sea. So we're limiting our spatial domain, and we're not fully coupling at this point that I'm discussing here. We use a 4-kilometer SICE model coupled with an atmospheric model, URI5, that assimilates ice information. So we have a very accurate data layer providing information from the top, and we couple it with a data layer from the ocean that is also very accurate in that it's a free-running ocean model that accurately is capturing the sea ice. So we want to just dig in a little deeper into the performance of SICE in the Bering Sea alone. And we find that we're able to couple them and accurately represent the evolution of the sea ice in the Bering Sea. Here I'm showing a very low sea ice year. It's historically one of the lowest, 2018 to 2019, where the ice didn't nearly advance as far as it should, as it does in a typical year. And the model performed quite well. We modeled 5 years so far, and in all those years it has performed well. If you want to quantify that, we show the ice area fraction in the Bering Sea on the eastern Bering Sea shelf for 2019 and 2020, and both in the low ice year and in a very typical sea ice year, the timing of the advance and the retreat of the sea ice is well captured. We also look at satellite products for the ice thickness and we recognize that SICE is capturing both the ice advance and retreat, but also the thickness distribution, both spatially and overall for both these seasons well. Where we run into trouble is if we weaken the coupling between the ocean data layer and SICE, which points to the need for fully coupled representation. So SICE will take the ocean state that it's given, and if in the standalone mode, it'll take an estimate of the mixed layer depth and use those two pieces of information to determine how much ice is formed on a time step. If you don't nudge hard towards an accurate ocean state, you can see that the volume of ice produced and the area concentration deviates rapidly from an accurate solution, pointing the need for a full coupling. So we do full coupling. So we've coupled SICE to Schism for the Bering Sea, and we like Schism as a model because we could go into regions with a very high resolution. We can look at, I'll check my time here, okay. Less than 2 minutes, okay. So Schism works very well for this situation. We could have very high resolution around the Aleutians and along the coast where we really want to get an accurate forecast. We first test Schism in standalone configuration during the summer to show that we can reproduce the temperature, the tides, the stratification evolution on the shelf. And we've shown that it does a good job at that. And we finally have coupled the 3 components and show that, and are starting to find that SICE and Schism work well in a fully coupled mode to accurately capture the sea ice evolution. Here again, we're just showing the beginning of 2018, the December 2018 winter season. So the next big step is, well, there are a lot of questions left, but a future step would be to expand our domain into the Beaufort, Chukchi Seas, and into the Gulf of Alaska, where the ice characteristics will be different, either because of fjords and freshwater runoff, or because of the multi-year thicker ice that you'd find in the Arctic. There's very interesting questions about wave current coupling and wave ice coupling combined, and how the ice may damp the waves, and how the waves might break up the ice that will present themselves as we go further into this. And there's very interesting questions as we consider inundation, wetting and drying, potential formation of Stamuka, where ice piles up on dry land and then grows larger during wetting periods. So there's a lot of exciting work left to come with this. I don't know if I should cover I will not cover my last slide, so I'll leave room for questions.
Thank you very much, Scott. That was great. Thank you. And as Scott also maybe did mention that, we also feedback on correcting sea ice cap and those things because of this tight coupling, and Ufuk also mentioned that, but great job, thank you. I don't think we have time for questions, so maybe we should directly go to the next presentation. Thanks.
All right, next up is William Randstrom.
Okay, great. Thank you. Let me share my slide here. Can you see the slides in the room?
Yes.
All right, thank you very much. Hello from Miami, so a big change from the Bering Sea. I'm going to be talking about hurricanes and the HAFS model, so some of our recent advancements for multiple moving nests and telescoping nests. So I'm working with my team of folks here at University of Miami CMUS and NOAA HRD at AOML, Luke Raymer, Andy Hazelton, and Gopal. And then we've had a lot of really important contributions from STI, the HAFS team at EMC, GFDL, and the oceanographers at PHOD here at AOML. In the interest of time, I'll just go over this one very quickly, but the objectives of our lab would work on a lot of different ways of improving hurricane forecasts, from developing next generation hurricane models, starting with HWRF that Gopal began over 15 years ago, using our aircraft observations to improve the model, as well as for situational awareness of actual events as they are ongoing, using these models to advance our understanding, and then transitioning them into research to operations. We've had a lot of success in the past with the HWRF, and now with the HAFS, we're going to be continuing with additional upgrades to the forecast modeling. The current state of HAFS, there are This is part of the Unified Forecast System. It's hurricane analysis and forecast. This has been a collaboration with AOML, EMC, and GFDL. We have two versions that are currently running in operations, HAFS-B and HAFS-A. These have been showing over the last several years in operations about a 15% track improvement compared to HWRF and a smaller improvement of winds compared to HWRF. The main subject of my talk today is going to be the multi-storm HAFS, the HAFS-M, which we are running in our real-time parallel experiment. We began running this in real-time parallel last year. So here's a graphic from several storms from last season. This is, for this season, we're running a configuration with 4 storms running as high-resolution nests at 2 kilometers. The parent domain is at 6 kilometers. This is a static parent domain that's covering the North Atlantic and much of the East Pacific. So this, is something that's also potentially helpful for some of the DA work, as Joseph would talk about. So we go into a static parent domain. In this configuration, we're running a 7-day forecast this year. So we have a longer tracks that we're able to forecast, as well as examine TC genesis. We're using vortex initialization based on TC vitals, and then cycle DA from the storm nests from prior runs. What we saw in our real-time parallel experiment last year, when we were running 3 storms in parallel, was about a 10% improvement in track once we got beyond about 36 to 48 hours, so the longer forecast period, and then intensity improvements on the order of 20%. I think this was a combination of factors from capturing the interactions between several storms in the basins. Much of the time during last season, there were several active storms at once. We think there's also some improvement, even when there's only 1 storm, just from having the larger parent domain at very high resolution to capture the flow in the tropics and the subtropics, so probably leading to more accurate track forecasts. One of the things we can compare when we look at how these models run, the HAFS-M is running on a domain that's about 125 degrees in longitude, 62 in latitude, summing up to about 2.2 million cells. The HAFS-B and the storm-centric domains in operations are running about 75 by 75 degrees with about 1.4 million cells. And when we take into account how the runtime performance of these acts, the blue line here in the graph on the right shows the core hours for the number of storms if we were running in the storm-centric. So basically, the single storm just multiplied by that factor. However, when we're running in the HAFS-M multi-storm version, we can start to achieve some real efficiencies in compute use. So as you go to 2, 3, or even more storms, we're consuming quite a bit less core hours. So when you get out to 4 storms, it's approximately the same amount of CPU time as is needed for 2 in the storm-centric. This season, a lot of the storms have not been very long-lived, but the one long-lived storm that has really been interesting to look at so far has been Hurricane Erin. This is the set of our 7-day forecast. And what you can see is these tracks really did a pretty good job at staying towards the west side. The best track is shown in the darker black, and these really gravitated towards what was the final track of this system. You can see here one of the examples from on August 13th. The maroon with the triangle is the HAFS-M, showing a much more westerly track than what you can see from the operational GFS in the blue. You can also see here the rest of the models only go out to 5 days. So when you have the 7-day forecast, you can really see where the storm is moving and that it's safely steering not only away from the Konas, but also away from Bermuda. And in comparison, you can look at, for the same lifetime of tracks in HAFS-M for Erin, down below, there's the GFS tracks, which show that there was a lot more spread on those, and many of those earlier forecasts were tracking it much, much farther to the east. So the HAFSM was doing, quite a bit better job for this storm. So what we're looking at with this real-time experiment, we'll have compiling over the season, these 7-day forecasts. This is the first time we've been running that in our regional model. We'll also be compiling statistics on the genesis tracking. This runs with fully cycled initial conditions and the MOM6 coupling. We're basically paralleling the half-speed physics so that will be easy to compare, sort of an apples and apples comparison. All these results can be seen on our storm.aoml.node.gov website, where the real-time parallel experiments, not only for this, but all of the ones run at AOML and at EMC are shown with comparisons to the operational HAFs, HWRF, and GFS. One of the pieces of upcoming work that we've just begun here at AOML is going to be telescoping moving
like
nests.
2 minutes. 2 minutes.
Okay, thank you.
Thanks.
So this development is going to allow us to have multiple levels of nesting, similar to what was there in HWRF. And the main goal of this is so that we'll be able to reach kilometer or sub-kilometer scale for the storm itself. I think another benefit of this is it'll really extend the range of what options of model resolution and compute capacity someone could work with. So, in operations, we will be aiming for the 1 kilometer resolution. This will also give someone in a more research mode a capability to do something like, say, run in a global configuration with 27 kilometers for the globe, 9 kilometer intermediate nest, and then a 3 kilometer storm scaled nest. This is work that we're planning to be doing over this fall and winter, with the hopes to be running a version of this in a real-time parallel for the 2026 season. So in summary, our operational targets for 2026 and beyond are to be capturing these multi-storm interactions to improve forecasts of intensity and structure and leverage the benefits of this large fixed outer domain. So getting some improvements in accuracy for that, as well as making it an easier platform to work on for the data assimilation side of the house. This also is possible using a reduced amount of computing resource compared to running many single storm configurations. In the longer term, we're looking at the telescoping nest to expand the refinement options. Our main goal, again, being sub-kilometer scale, where we'll have the telescoping nest will first be enabled, then we'll also be working on physics changes to have a coherent suite that can capture the processes at those scales. Also looking at the cyclogenesis this year in the current run, and then in the future, looking to initiate nests for pre-invest from the tropical weather outlook so that we can give some high resolution views for guidance for forecasters as well there. Finally, some other things in terms of the hazard side, looking at accumulating hazards across multiple scales, multiple cycles, such as precipitation or wind swaths, and then leveraging the fixed outer domain to improve data assimilation and have a more stable platform for that. This is my final slide. Thank you. So here's just a link for, again, our viewer and any questions if there's time left.
Yeah, thank you very much, William. I think you're over. Yeah, let's have a round of applause. Yeah. Thank you. So please post your question to a Slido so William can help with answering, and let's move on to the next presenter. Thanks.
And our next presenter is Saeed Mamari.
Awesome. Thank you. Good afternoon. My name is Saeed Memari. I'm a postdoc at Colorado School of Mines, and today's presentation is about the real-world evaluation of UFS coastal application and two-way coupled wave circulation modeling during 2021 hurricane season. And at the beginning, I want to thank my co-authors for their contribution. Accurate coastal forecasts are critical for...
Don't have a presentation yet.
No. Perfect. Accurate coastal forecasts are critical for safe navigation, infrastructure, and hazard preparedness, but many operational systems will rely on uncoupled or rigidly paired models, which limit accuracy. Our work addresses this gap by testing NOAA's flexible UFS coastal framework in real-world case at New York Harbor. New York Harbor is both challenging and well-observed system, making it an ideal case study. It has complex bathymetry, high navigation traffic, and is exposed to hurricanes. This place was also designated as NOAA UFS CAT testbed region. Importantly, this work represents the first real-world evaluation of one of the first real-world evaluation of the UFS coastal application in an operational framework. We applied the system in a hindcast for summer 2021 during Hurricane Elsa, Henry, and Ida. In this study, we used the UFS coastal framework, which connects hydrodynamic and wave models through a mediator. The active models are Eskism, a 3D unstructured hydrodynamic model, and WaveWatch 3, a spectral wave model, also unstructured. The mediator component, CMAPS, handles the data exchange and synchronizes the coupling, while the CDEPS, the data component, manages the external forcing data, such as atmospheric inputs. The coupling is two-way. Eskism provides currents to the wave model, and WaveWatch 3 returns radiation stresses back to Eskism. This setup allows us to capture realistic wave current interactions within UFS system. Here are the details of the model setup for hydrodynamic. Eskism uses around 61K nodes and up to 31 vertical layers. WaveWatch 3, on the other hand, has 21K nodes, so a smaller, coarser mesh. They have different boundary conditions and atmospheric forcing, and the simulation period starts as June 1st up to September 30th, 2021. And on the left figure, we see the WaveWatch 3 mesh, and on the right, we see the Eskism mesh. And in the middle, we see the differences between these two mesh. The middle top is for WaveWatch 3, which has coarser mesh, and middle bottom is for Eskism, which has much higher resolution. We tested 3 setups: uncoupled hydrodynamics, uncoupled wave, and a two-way coupled system. Coupling was set up with bilinear interpolation at 900-second interval, exchanging currents from Eskism to WaveWatch and radiation stress back. To confirm, so the first thing we did is to confirm that the coupling was functioning. So we compared the coupled and uncoupled output. On the left, we see the velocity from the hydrodynamic, and on the right, the scatter plot, we see the significant wave height. If these values follow exactly on one-to-one line, means that it's not two-way coupled, they're not exchanging data. But the small deviation, as we see, it confirms that the two-way physics are active. And then we move to the validation of the waves. Figure on the left shows the significant wave height top, and at the bottom is average wave period. At the location of the buoy shown on the map, the boxes shows when the hurricane happened. The black line shows the observed data, blue is uncoupled wave, and the red is simulated two-way coupled wave. And overall, both models, uncoupled one and two-way coupled, they produce very good results. But for the two-way coupled, we see better performance in terms of RMSE and bias, and especially for the wave period. And if we want to focus only on the hurricane periods, we can look at the figure. A scatter plot on the right shows significant wave height and average wave period comparing uncoupled and two-way coupled, and we see that the two-way coupled, the blue dots, follows the one-to-one line better compared to the yellow one, which is for the uncoupled wave. And if we move to the validation of the hydrodynamics, we see the good agreements with observation for water elevation, water temperature, and water velocity. most of these observations we see, it's shown on the map, they are at the shallow areas and in the channels. So the effect of waves are very small in those regions. And that's why there's no clear improvement in terms of hydrodynamics when we use a two-way coupled model. So there's no quantification of that. And the reason, as I mentioned earlier, is that most of these stations are in shallow, fetch-limited areas, which limits the wave-current interactions. But if we want to compare the two-way coupled and uncoupled wave in both space and time, we can basically say the differences of the two-way coupled and uncoupled from the space. On the left figure, let's focus on that. The left figure shows the maximum absolute wave height difference between two-way coupled and uncoupled. And we see where those maximum values are, which mostly as the inlets and deeper offshore regions. And it can be up to 0.5 meters. In shallow areas, the depth is 20 meters. We see the difference is minimal. So the time series on the right is the 95 percentile range shown in shades. The blue is for the shallow area, less than 20 meters, and the red is for deep area, above 20 meters, and the median is shown with bold lines. And again, we see that most of these wave differences are happening at the offshore regions and not at the nearshore areas. And we do the same thing for the hydrodynamic, and let's look at the water temperature differences. The differences are small, within plus minus 0.5 degrees. Shallow areas, again, it's narrow spread. The differences are not as high as the offshore areas. And the histogram on the right shows the distribution of it, which is centered around 0, and the most values fall between minus and plus 0.3. So basically confirms that the hydrodynamic impacts are weaker compared to waves. To wrap up, we tested one of the first real-world evaluation of the UFS coastal application in operational framework. We used two-way coupled wave and hydrodynamics for New York Harbor. The effect of the two-way coupled was more significant in waves compared to the hydrodynamics, and it confirms that the coupling framework is active and physically consistent. Thank you.
Thank you, Said. We have time for question. Yeah.
So do you, did I see it correct that you only put the currents from Schism into WaveWatch and not the water levels?
Yes, so the current version that I'm using, it only passes currents from Schism to WaveWatch. But in reality, it should have also passed water level, right? But in the current setup, it's only currents.
Yeah, so the fact that you see very little impact of the coupling on the coastal, on the nearshore waves, is probably an artifact of the fact that you don't do the water levels.
It can be also that, but to make sure I should test it and then quantify it. But that might be one of the most important reasons why it's happening like this.
Yeah, thank you.
Thank you.
Yeah, I think that was, I guess, an issue with the cap. I think that is resolved right now, right?
We are using the significant wave height at this point, so you can couple with that one too. Yeah, we have some configuration. I think you found. Yeah.
Yeah, thank you, Said.
All right, next up is Joseph Zhang.
Can you hear me?
Yeah, we can hear you. Hold on
is
1
it
second.
slides?
We're getting your, oh yeah, there you are. Can you share your screen?
Yeah, I'm sharing my screen. Probably have to
It's good to see you
redo
even
it.
virtually.
I'm sorry I couldn't come in person. It looks like a very fun meeting.
It is.
Is
All
this
right,
better?
there you go.
Ah, great. Well,
Yeah, but
good
we're seeing it in presentation mode.
Yeah, this is a presentation mode. Let me see
Or
swap.
not in presentation mode.
How about
Yes, that's
this?
it. You got
Okay.
it. Perfect.
Great. let me get my pointer. Good afternoon, everybody. So this is like a project report for the ongoing CCOFS project. And this is a multi-year project. We're in the third year. So I'm Joseph Zhang from Virginia Institute of Marine Science. I'm leading a team here. But I want to emphasize this project is really multi-organizational collaborations between the WIMS, NOAA, and the UCAR. Okay, so we work very actively with co-ops folks, OCS folks, and the IUS folks as well. So I want to emphasize that. Okay, so the overarching goal for this CCOFS project, the BIL project for the Southeast Coast, is threefold. First, we're going to use this opportunity to bring up a new 3D operational forecast system for the Southeast Coast plus Puerto Rico. We call it CCOFS. Second, we want to use this opportunity to really do some testing about the emerging and the exciting UFS capability. So that's why all of us are here. Okay, so and the last one is to use this opportunity to really update the co-ops skill assessment. I think somebody yesterday talked about this. So this project will provide multiple benefits to the coastal communities, including coupling with hydrology, the national water model. So this is something we do with CCOFS, with staffs, and this will serve as a real world test for the UFS for model coupling and skill assessment. We touched that, safe navigation and blue economy as well. So the CCOFS will cover the southeast part of the United States and from the Virginia to the Florida Panhandle. And in addition, this is something we did very differently. I think it's the first time we use SCISM to cover the disjoint domain. Okay, so Puerto Rico and the Virgin Islands. So in terms of offshore boundary, we set ocean boundary at 100 meter, roughly 100 meter isobars for the East Coast and the 1 kilometer isobars for the Puerto Rico and the Virgin Islands. And on the inland side, we closely couple with the national water model. So you can see those thousands of streams from the national water model. They inject the water directly into the SCISM domain, and the SCISM will be in charge of routing that water and also water from the direct precipitation, inside our domain. So we cut the land boundary 10 meters above the sea level so that to minimize the backwater effects and also make the coupling with our national water model much easier. So yeah, I mean, every time I give a talk about the SCISM, I always want to emphasize the importance of DEM. For this is no exception for CCOFS. So for CCOFS, we use a variety of DEM because of large spatial coverage. So what we found is that we tested a variety of DEM sources, and we found that none of them really the better than others, in all domains. Sometimes Blue Topo is best, sometimes CONET is best. So we really have to test it out, especially for 3D. For water level, not so much for water level, but for 3D, this is absolutely essential. So that's our first lesson. And everything we do is documented by the Python scripts. So, we can send these whole packages to NOAA, and they are able to reproduce everything we do. Okay, so and the one thing I want to emphasize is that once we load the DEM onto the mesh using the linear interpolation, we no longer manipulate the bathymetry. So this is something I keep emphasizing. I think the more and more users are starting to realize this is actually a big deal. So we recently, Ocean Modeling Journal has a collection of SCISM-related papers. So last year I published this paper. So I think this paper really reviews and summarizes our philosophy very well. So if you are interested in, why we're doing this type of practice, well, why we, do not, why we not the smooth bathymetry, so why bathymetry is so important as a first driver of coastal applications, I would encourage you to take a look at this paper. So yeah, I think Dan after me will talk about the detail. I will not get into the detail of the components. Suffices to say that we went through a lot. It's not easy task for us. We thought it's easy, but it turns out there are various issues with the UFS camp related to unstructured grid. We had to really spend lots of time sorting out all those kind of issues. Related to the domain decomposition, related to the unstructured grid topology, for example. But the short story is that we are at a stage we are able to directly couple with other models like the WeWatch3. So this plot here shows the WeWatch3 domain, which covers the CCOFS domain. So the two models have different domains, and in terms of grid size, WeWatch3 is about 1/3 of Schism. But you can see that in terms of the resource, the wave model always consumes more resource. That's not surprising. And one thing we found out very interesting is that the UFS at the moment, for unstructured grid, still not very efficient in terms of domain decomposition for whatever reason. Okay, so finally, that's why we decided to just use static partitioning, just turn off the dynamic partitioning, and then, we were able to get a pretty decent performance, compared to standalone models. You can compare this; it's almost the same as
Joseph,
standard.
it's
Yes,
like
please.
less than 2 minutes. Thanks.
Yes, I will speed up. Yeah. Anyway, so yeah, we went through all these steps, and it's very important to take baby steps and check all the exchange variables one by one, and those plots shows the difference between coupled and uncoupled models, right? So so we are starting to get some sensible results, and obviously we need to go into the more details, especially there's some future work related to 3D vortex coupling. So this is going to be another 3D OFS for NOAA. So we understand that it will be used for the safe navigation. So we need to do a serious validation for the current velocities. Previously, we have done this for Chesapeake Bay, Tampa Bay, St. John's. But the observation, ADCP observation, especially lacking in Charleston and Savannah. So co-ops teams collected the new ADCP data, in summer of 2023. So that's great news for us. So we did some validations. So the long story short, okay, for Savannah, we were able to get a pretty reasonable results with minimum tuning. So the most challenging one is the upstream, which is not surprising. The most upstream one is most challenging. So we had to really, what we found is that there's a large uncertainties with the DEM in the marsh areas, especially the marsh channels. So we finally decided to just keep the channels, all the channels, but they essentially make the other areas of marsh, more or less permanently dry. So that resolves these salt intrusion issues. So yeah, so the CCOFS is now being pre-operationally tested in the NOAA co-ops. So here are some of the performance data. So boundary condition, initial conditions, from HER and GFS, and from the GRTOFs. So that's the forcing, and the co-ops is starting to look at the skill assessment, for water levels, temperature, salinity, and velocity as well. So, and independently, we're also working with the IU's group to really do some basically test this CCOFs inside the sandbox. So the idea is then to speed up the research to operation, right? So that all parties have access to the same platform, so we can test collaboratively. So here are this table shows some of the performance data. I won't go into detail. They even
Joseph,
potential for,
you're kind
yes.
of out of time. If maybe
Oh,
10 second, 15 second, you
yes,
summarize. It's
this is second last. Okay, so anyway, so just quickly summarize, we are working actively with IUs and co-ops and OCS, UCAR, and Sicora to bring up a new forecast system. And we use this opportunity to really actively test the coupling with the national water model and coupling with the WaveWatch 3 and etc. using the UFS. So we are actively working on a skill assessment, especially for 3D processes. So each system is unique. So we need to do site-specific validations. And lastly, we welcome the community feedback. I'll stop here.
All right, thank you.
Let's give a round of applause.
Round of applause.
We have to move on to the next.
Yeah.
Thank you, Joseph.
Thank you, Joseph.
Thank you. Thank you.
Yunfeng's son is up next, and he is virtual. All right. Go ahead and share your screen. He'll be talking about the development and implementation of regression tests and applications in the UFS coastal framework. Okay, he's already got it up. All right.
Can you see my screen, Tracy?
Yes, I can. Can you do the slideshow?
Sure.
There you go. Oh, perfect. You're good to go.
Okay, thank you, Tracy. Good afternoon. My topic is development and implementation of the regression tests and application within the UIFS coastal framework. So it is a teamwork and have been to the effort of a great community here. So I will present this regression test work here. So firstly, I will briefly introduce UIFS coastal. Saida make an introduction of the UIFS coastal yesterday. So here I will be very briefly to introduce. And the second one is the dark case, which is our systematic experiments of the regression tests. And the third one is the scalability and then the summary. So firstly, for the coastal hazards, it's like storm surge, flooding, wave impact cause buildings in damage and threaten to lives every year. So the photo in the right is the damage caused by Hurricane Sandy to the New Jersey coast. And accurate forecasts in the nearshore zone is especially challenging due to the dynamic wave current interactions. And to be an accurate model, the model should be reliable, consistent, reproduce observed conditions, reproducible, same setup yield to the same result anywhere, systematically evaluated, standard test against the real world data. And here's the UIFS coastal. UIFS coastal is forked from UIFS weather model, adding the coastal ocean models. It's a modeling framework for coupled coastal application and regional forecast. And for today's regression test, we are using the wave part WaveWatch 3, the ocean part schism, and also the sea depth part, the data atmosphere and the data ocean. The objective here is to firstly design standardized regression test, use high quality observations during the Hurricane Sandy at a dark region. The second one is evaluate multiple model setup, the hydrodynamical model, the schism wave model, WaveWatch 3, and the fully coupled wave current interaction model. Third one is to access the coupled strategy. Here we have two-way coupled case. One is the radiation stress coupling. So it's very traditional 2D coupling. It's a Lanhagen coupling. The second one is the vortex 3D coupling. And the fourth one is demonstrate the scalability by to apply the UIFS coastal to larger domain. And here, why we choose a dark regression test? Firstly, is the dark region, how the longest continuous coastal wave current data set in the US. It has the dense instrumentation, it has the tidal gauge, ATCP, buoy, and wave spectral observations. And it's also very popular, recognized as the international testbed for coastal processes. The photo shows this facility, the FRF facility, and also the coastal and observation sites here. And this figure here is shows our study domain and the dark region. Firstly, this is studying the Hurricane Sandy case. The Hurricane Sandy is started from the Caribbean Sea and moved to the northward parallel to the US Atlantic coastal line. Then it turned northwest towards the mid-Atlantic region. And because it's a trajectory, so it make a big damage to the coastal region. And here, the panel B here it shows our study domain and the grid system for both WaveWatch 3 and the schism. So we designed a series of experiments to drive this Hurricane Sandy case. The case one is the sea depth plus WaveWatch 3 with only the surface forcing, which is the surface wind and the air pressure. The second case is sea depth, the ATM plus WaveWatch 3 with not only the surface forcing, also the sea level forcing to the WaveWatch 3. The third case is like the ATM plus schism. Fourth one is the two-way coupled schism and WaveWatch 3 with radiation stress coupling. The fifth is the most advanced vortex 3D coupling. So here is like show the structure of the 2D coupling, which is the radiation stress coupling. In this case, ocean gave the WaveWatch 3 the sea surface current and the sea surface height, and the WaveWatch 3 gave schism the radiation stress. So it's a very simple give. So here it's like wave radiation stress is uniformly distributed to all layers in the ocean model. So it's the older two-way coupling. And here we introduce the new 3D vortex coupling. So in this case, so the wave gives the Stoke drift stress to the ocean, and it has the impact in different layers of ocean, and also make the surface layer and the boundary bottom layers to be a real 3D two-way coupling. So here I will show some of the results. So this figure is the water level. So
less than 2 minutes.
Oh, sure. I will speed up. So here it's like it shows the water level simulation. It's a match with tidal gauges in different tidal gauges, and also it provides the reliable baseline of the hydrodynamic conditions. And here, this figure shows the significant wave height, the mean time period, and the mean direction of wave for the different wave models. So this figure shows vortex 3D coupling is the best results. And here is show a very clear figure for the along shore velocity and cross shore velocity for the Long-Hagen coupling and the 3D vortex coupling. So it shows 3D vortex coupling shows a very clear cross shore velocity in intrusion to the domain. It has a better representation of the surf zone circulation. And here for the last one, so we have demonstrated it have very good results on the dark case. So here we are trying to expand it to a much bigger domain. So this is for the hurricane Ian in the Atlantic domain. For this part, we only finished the 2D, the radiation stress coupling. So for the vortex 3D coupling is still in progress. For the summary here, firstly, the standardized regression tests provide a foundation for reproducible, reliable coastal modeling. Coupled strategy method, vortex forcing improved nearshore resistance radiation stress remains useful for efficiency. UIFS coastal scales effectively from local test bed to regional like Hurricane Ian. The CICD practice are adopted within UIFS coastal development process to systematically integrate and validate model changes. This work strengthens UIFS coastal's ability to forecast storm surge, coastal flooding, and wave dynamics. Thank you.
Thank you, Yunfeng. Let's give a round of applause. Thanks a lot. So again, we are at the time, so please post your question to a Slido. Thank you, Yunfeng.
Thank you.
All right, next we have Dan Yu. And the title is Recent Schism Coupling Development under NOAA's UFS Coastal Framework. Dan, can you share your screen?
Yeah. Can you see my screen?
Not yet. Oh, now I can. Yeah, now go into presentation mode.
Oops. Okay. How come I cannot? Can you see it? Maybe this.
You're almost there. You're almost there. You're getting closer. You got it. You got it. All right, take it away.
Yeah. Okay. Good afternoon, everyone. My name is Dan, and today I'm gonna talk about the recent schism coupling development on the UFS coastal framework. And first of all, this is the teamwork. I would like to thank all the team cooperator here, and thanks for all the help to make this happen. And I have some slide maybe just similar like Yunfang and Joseph have here. I will just quickly go through. So the development here, we mainly focus on the skis and try to engage the other model like such as WaveBus 3 and other components. The focus here, we are developing this to couple with WaveBus 3. And from the sea depth size, it's feeding the surface forcing into the both model, and for both model they share the same input from the sea depths, and we focus on the exchange variable between the WaveBus 3 and the schism. And as you can see here, this is same slide, but I just simplify here, and we focus on two different type of coupling. First one is Longhiggen coupling, then the second one is vortex coupling. So we want to make sure all the exchange variable are properly from WaveBus 3 size can deliver to the schism site. And again, this is the team effort work. And here I would like to ask thanks Ufa from UCA and Ali from AMCO and Yun from Dennis from NOAA to make help me to test this coupling. And we start from this test case for the Sandy case. During this development, and we actually encounter several issues. First, we encounter some ESNF triangulation error, and since Bob Wufu from UCA helped us to fix this error, and right now this error already been fixed. In the meantime, original Schizon cap only deliver the air pressure and wind speed. Right now, after this development, all the surface forcing flux variable are being added into the cap. And we find out some certain issues when we add this cap. And these issues will sometimes will cause model unstable, and this cause some like ice coupling might blow up, and so after we figure this out, and we also fix this issue. So this development also benefit to the size coupling, and as you can see, we do the two different type of coupling. There are like 10 variable we need to check carefully. So the approach here, we actually Schizon, it has its own wind wave model. So we start from Schizon wind wave model standard alone and compare with this Schizon and wave velocity coupling, compare its value carefully. And we found out there's some certain issue in wave velocity cap. And for example, like along the boundary, we have some zero value, and this already been fixed, and some orbital velocity, and looks not right. And so we also found out some other exchange variable like Stokes velocity, and has some we need to be further checking. And so right now we will consult other model developers like Aaron, Ali, and John Warner to discuss and fix this code. So for the current status here, right now Long-Higgin coupling now works under the UFS coastal, and vortex 3D vortex coupling need further development. So after we done this smaller test case, dark case, and we apply this test case to the CCOPS domain, just like the presentation just gave, and we do a 1 month simulation test and check its result. And this again, this is the same slide. I won't. So we put the elevation and wind here, and for the wave boundary, we put a spectrum density, and only simulation 3 days, and we do two-way couplings. And this is the result from the buoy for the synchronization wave height. So both buoy, the model shows for both coupling, they deliver the reasonable results. And as I mentioned before, this is the some variable we try to compare with the wind wave model. As you can see here, is they deliver different values and different behavior, and we'll keep work on this. And this is the large domain test case here for the CCOPS couple case, and this for Atlantic domain is here, and the solid line here is a CCOPS domain. We run 1 month and Long-Higgin coupling for 5 minutes every coupling. And in very beginning, when I tried to test this, I realized this the parametric life actually affect the efficiency a lot. So after a few trying, and I figure it out, and then and when I turn this off, I can get very decent efficiencies here. So for the 1 month run, I can finish within like 6 hours, 7 hours. So and we also check carefully for the exchange variable.
Dan, like
yeah,
1.5 minutes more or less.
Oh, okay. Okay, and this is some significant wave height validation. As you can see, it's quite reasonable. And this is wave period. And this is for the wave direction. So all of the scale, they are reasonable. And we also can see the coupling effect here, and we compare with the standard long schism. So in summary, schism wave watcher now is work, and we'll put the dark case in the regression test. And all the tests, they can deliver the reasonable scale, and we can see the coupling effect. Also, we see this, we gain the reasonable efficiency, and with this works, and just like Scott present here, and this coupling will also benefit to other components. And on the right-hand side here, we also try to test with other components. This is some simple test that we with FV3, and we check the every exchange variable, exchange property, and we'll keep on doing this, and that's it. And thanks for your attention.
Thank you, Dan. Let's give a round of applause. Maybe one very quick question, if you have. No. Okay, Dan. Thank you very much. We need to move on to the next speaker. Thank you.
Sure.
The next speaker is Ali Abdelali.
Okay, I cannot share my screen. Oh, it comes. Oh, hold on a sec.
There you go.
Do you see my screen?
Oh, yeah.
And do you see it in the presentation mode, or I have to swap?
Yep.
It's in the present. Is it?
No,
is
it's
it-
not. It's not yet.
Mhm.
Yep, swap. A little back to the left. Left,
Okay.
left, left. Those arrows, you hit those arrows.
Okay, I do not see them. It's yeah. Okay.
We can see them, Ali. Yes.
Yep,
Okay.
yep, yep. Just click.
No. Okay. Okay. Let me share my other screen. What about now?
Oh, you got it. That's perfect.
Okay. Okay, so hello everybody. This is Ali Abdelali. I'm from U.S. Army Corps of Engineers, Engineering and Research Development Center, and here is the list of my co-authors. So what I'm doing here, although I have been working with UCAR and also with NOAA for years, I left those organizations I think 3 years ago, but I have been actively working with NOS. Within UFS and also for UFS weather model for the global applications. So this presentation is a touch on the work that we did in WaveWatch and also an introduction to a new model that we developed. So I will explain to you why we decided to develop a new model rather than WaveWatch, although we invested a lot on unstructured capabilities of WaveWatch. But we realized this is the time that we need to move on to a new model. And I will explain to you momentarily why we decided to do that. So,
Ali, try to leave a couple minutes for questions. I have a feeling Hendrik's gonna have some.
okay.
She was just kidding.
Okay, this is 4:40, so I need to go and
So
pick up.
if you
the
finish by
comeback.
7 minutes, then you will get 2 minutes of question.
Okay,
But anyway,
no
yeah,
worries. Okay.
up to you.
Anyway, so over years, I think we have developed the unstructured capabilities of WaveWatch, and the reason we did those because we wanted to push the envelope and we wanted to push the boundaries of WaveWatch to have more efficiency and accuracy. We implemented WaveWatch We implemented new parallelization to get rid of the maximum number of CPU count that we could use. So people could use thousands of CPUs for simulations. But over the years, we realized that development needs some refactoring. We need to modernize the code because the model is not optimized. It is written in Fortran, and unfortunately, there is no longer Fortran developers in the academia. People are not learning Fortran, so we needed to have programmers, and we couldn't find good programmers. And then we realized that also our regression testing is lacking lots of problem. Like we cannot test everything on the fly, and we realized that we need to modernize the code. So lots of if-defs. I think many people in this room can confirm that if you want to debug WaveWatch, even if you are the developer of that part of WaveWatch, it's very hard for you to find the reason, because I think it's buried under lots of if-defs. And I think because it's a community model, people just put things in the model and they don't care about the performance. And after a while, if you don't check them carefully, then it goes nuts and you cannot get the same performance as before. So what we did is that over, I think, the last year, we developed a new version that is written in C++, and we wrote it in with the latest coding practices. So I think people coming out of the universities can leverage our work. And then we put all the source terms and the properties that we implemented in WaveWatch in unstructured in this new model. And the end goal is also adapting that to GPUs, because we wrote it in C++, it's gonna be very easy for us to port it to GPUs. So we named the CPU version of this model Triton C, and in the future, the Triton G, which is the GPU version of that, will come along the way. Also, we developed lots of auxiliary tools for validation and verification, because lots of new sets of observations came on board, and we needed to have all of those implemented in our validation and verification, particularly for coastal scale application. We also added the light and effective regression test system on the fly during the compilation, so you don't need to run those excessive outdated regression tests of WaveWatch. And then we also are trying to implement the physics optimization, a very efficient version of that, and also data assimilation and integration with AI and machine learning. So over years, I think over 10 years, we implemented different types of domain decomposition, including Scotch, Parmetes, and the new partitioning system that we developed ourselves. We implemented implicit solver, including Jacobi and block-Gauss-Seidel method, which can help us with the CFL constraint. And also with the domain decomposition, we are not limited to almost 1,000 CPUs, so you can allocate 10,000, 20,000 as far as you have those CPU cores. And then we added lots of shallow water physics, like the vegetation, diffraction, depth breaking with rocky beaches, triad interaction, improved them, wetting and drying, and etc. And then also we added some limiters. We improved the GSE correction and also OpenMP for unstructured. But as we moved further, we realized there are lots of limitations. For example, we implemented the unstructured capabilities for the Great Lake in operation at NUA. But the problem was, for example, that the operational center didn't let us to implement a model which is not binary identical. So we had to switch back to some of the old version of our unstructured capabilities, although we could go down to 10-meter resolution. You can see the meshes here. We demonstrated how the results improved over switching from the coarse resolution 2.5 kilometer to 250 meter to 50 meter to 10 meter. But at the end of the day, it didn't get implemented. And you can also see here the carded limit that I mentioned, the number of CPUs that didn't let us to go further. We also further implemented wave vegetation interaction, and we tested that extensively with the field observation and with laboratory cases. But because we are developing the model very fast, and the code management, the centralized code management was not able to keep the pace with us, the model is not merged and integrated to the mainstream, and after a while we couldn't maintain the code integrity with the developed version of WaveWatch. So we are in a situation that we had to make a decision. Do we want to continue this, or do we want to go and modernize everything and also have more control on the development? So also this is one example of the GSE effect that you can see on the left-hand side, and this is in operation. All the day, if you look at the GFSV16, you can see the GSE effect in most of the forecast results. We did the coupling with a schism. I think you have seen a lot of talks about those. We ran the model on a standalone global scale, multi-scale, from very coarse resolution to to high resolution in the coastal areas. And then we also designed tools that can generate unstructured meshes on the fly for wave models, for spectral wave models. And then we tested that for swell, for infragravity wave, for wind waves, and etc. And then to name a few more applications, the USACE Wave Information Studies, the very famous one, it's going to switch to unstructured capabilities. Also the GFSV17, before I left NOAA, I think I demonstrated the capabilities and it's on the way. Also the RWPS, which will replace the NWPS, I think it should also switch to unstructured capabilities of WaveWatch. Recently, we published a paper about how we integrate all types of observations, from satellite altimeters to drifter buoys and NDBC and CD buoys, the stationary ones. And we are working on integrating also the coastal SWAT and CFO-SAT, the satellite altimeters to have the validation with
Ali, at like almost 2 minutes.
Okay. So these are different types of observations, like the SWAT satellite. I'm just skipping those for the sake of time. And these are the validation between the observations and the model outputs. Very great performance. And then this is Triton C. So I just explained this graph for you, which shows that the red line, the vertical red line, is the Triton, is the WaveWatch cardec limit. You cannot go beyond almost 1000 CPU. The lower gray line, which is the WaveWatch with the squares, are the WaveWatch performance, and the upper plot with the diamonds are the Triton. So you can see you can allocate 10,000 CPU. You can run a 10 million, 20 million grid with domain decomposition that we implemented, and also it is more or less 4 times faster than WaveWatch without any optimization. So these results are very promising. As I said, we implemented on the fly during compilation regression testing for all of the physics that we have implemented, and we are planning for the GPU implementation. This is side-by-side comparison between the regional case, WaveWatch and Triton. You can see still the GSC because we didn't activate the GSC correction. And in the lower panel, you can see the global scale application. And then in terms of validation, the left-hand side is WaveWatch. The right-hand side is Triton. Without any optimization, you can see Triton is doing way better than that, especially in higher latitudes. And for the NDBC, for the stationary buoys, also Triton is doing better. All of the statistic metrics are in the presentation, and you can take a look at them later on. In summary, we are seeing superior multi-core performance compared to WaveWatch, although WaveWatch is also, the unstructured part of WaveWatch is also developed by us, but we dare to question ourselves and criticize ourselves to see, do we want to continue the development and face all of those challenges, or we want to switch to a new model. Also, we are working on the hybrid implicit-explicit to take advantage of such efficiency, and then also have some pre-computation if there is no current field, so we can gain some advantages. All the shallow water physics are implemented, and then we are testing Duck, North Carolina testbed and Oregon's testbed for coastal scale and also for infragravity waves. We are coupling our model to other models like ADH, our in-house flow model, with sea ice and schism on the way. We are planning on those and continue to collaborate with our colleague at NOS and in academia to make it happen. And we also invite all the participants of this workshop plus NOAA to take a look at our model. And if they are interested, we can collaborate on the development. We are also working on the physics optimizations using PEST on the fly, and then also with the GPU implementation of that, and with all of the new types of observations that we have, like SWAT, CFO-SAT, and DART for IG bands. So I think I could finish it in time, hopefully.
Yeah, but we don't have time for question.
Well, we have 1 minute, 1 minute, 1 minute.
Okay, so give round of applause for Ali, please.
Yay, Ali.
Okay, so Tracy really advocating for one question, so please, 1 or 2 questions.
I do.
So, for the record, Ali is completely right about the fact that the WaveWatch codes need to be optimized. So, him and I, we are on completely the same page. With that, we are on the NOAA side about to start to develop the next version of WaveWatch 2. And the fun part of this is that since we're all have learned how to do modular coding pretty well. I've been talking to, not to Ali, but to Aram, and it would be really easy to get the C++ code in tentatively back into WaveWatch 2 and all this kind of stuff. So I'm just looking forward to some really fun competition with this stuff. And it is a combination of competition and just practically being smart about this, because we are all using building blocks that are community codes. It means that if Ali and his group find something new that works better, or the other way around, we very likely will be able to exchange these things very easily between the models. And this is something that we started with a NOD project in 2008, when we started to learn how to do wave modeling as a community. And from that moment on, we also had Swan and WaveWatch exchanging stuff very easily. So looking forward to it, Ali.
Sure. I'm at UMD, so whenever you want, you can walk into my office and we can compete.
Yeah. Thank you, Ali. Thank you, Henrik. Yeah. Maybe
All
we can
right.
move on. Yeah, thanks.
Yeah, last talk of this session, and it is in person. Catherine Newman.
Okay, well, thanks everyone for sticking around. I'm Catherine Newman from NCAR, and I'm going to be giving a little bit of an overview of some of the work that we've been doing, establishing verification frameworks for for evaluating HAFS forecasts. I want to acknowledge my co-authors and also mention that this was done under the Developmental Testbed Center. All right, so since this, the main focus of this framework or this talk is about the framework that is built on MET+, and this is a little different session than I normally speak in, I thought it would be good to give a little bit of an overview of the MET+ software for those who are unfamiliar. So MET+ is a highly configurable verification framework that spans a range of temporal and spatial scales. It's community software, extensible, scalable, and has over 150 statistics and diagnostics for point and gridded data sets. As a community software, it has user support that's provided via GitHub discussions, and it has a library of use cases that are provided for easy spin-up. And it provides a versatile toolkit that enables objective and reproducible evaluations over a broad range of weather and climate applications. So if you look down in the lower right, that's a schematic of what MET+ is. So it's the statistical engine is MET, or the Model Evaluation Tools is what that stands for. And MET+ is basically the ecosystem that has Python wrappers, a database, and analysis tools included. Where did that go? There we are. So this is a quick look at the model evaluation tool. So this is the statistical engine behind the MET+. And the diagram here is showing all of the different tools that are included in the MET software. The different oval colors are showing some different types of tools that are preprocessors, regridding, statistics, analysis, those types of things. You can look at that legend there. But I want to orient you to the bottom part of the diagram where we have a number of different TC tools. And so for the purpose of this talk, I'll be focusing on, there's just 4 different tools that we've added into this framework: TC pairs, TC stat, RMW, and RMW analysis. But I also wanted to bring up that there's a number of other tools that are looking at continuous and categorical, probabilistic, ensemble statistics. We also have object-based. There's a whole slew of things that are relevant to TC forecasts that I'll be mentioning here as I get into the later part of this talk. So as far as this framework, the primary goal is to facilitate the rapid and straightforward comparison of experimental configurations and operational baselines. So we've been asked to add MET+ to the HAVS verification, or the HAVS workflow, with the intention of having it available for HAVS developers and community researchers, as well as our internal teams that are doing testing and evaluation, as well as decision makers for looking at prototype configurations for operations. We are following unified approaches for incorporating MET+ across the various UFS application workflows, and the purpose is to enable the use of MET+ for HAVS community developers to support the rapid performance feedback on innovations. So a quick look at where things stand right now. So this is the HAVS verification workflow, is what we're calling it, the HAVS VX workflow. And this is a Rakoto-based workflow that is running MET+ verification within HAFS. And so I'm showing here basically two different workflows. So the HAFS on the left-hand side is just a very simplified schematic. It's not the actual HAFS workflow, but that's representing that. And then we have this separate workflow that's running HAVS VX. And so the original intention was to actually plug the tasks into, the verification tasks into the workflow the way it's done in the SRW app. But after learning from the experiences of that group, we were advised to actually keep them separate for a number of different reasons that I'll talk about here in a few minutes. But this basically will run parallel to the HAFS workflow so that you can basically, as the forecasts are available, that dependency would be met and then it would kick off the verification. You could also stage an entire like 3-year retrospective or a season of data and then run the verification workflow off of those data sets without having to run the entire HAFS workflow. So this basically enables a real-time or retrospective type of mode for the verification. And then I'll also mention that we're employing different tools like the unified workflow tools that would generate experiments from a YAML config file. All right, so I mentioned those 4 different tools that are currently in the framework. So the first one is based on computing track-based metrics using TC pairs and TC stat. So TC pairs and TC stat are the 2 original like MET-TC tools that were developed over a decade ago with the intention of reproducing NHC verification. So it basically works off of an ADEC and a best track and has all of the different filtering and stratification options that you would find in the NHC verification system. So you can reproduce that verification. So you get track and intensity, wind radii, error, different skill and relative performance metrics, and then you can also have rapid intensification, consensus forecasts, all that kind of thing. The other tool that we've added is the TC RMW and TC analysis or RMW analysis tools. And what these do is they regrid the model data into a moving range azimuth grid that's centered along the track, the storm track. And then it also will aggregate those files and do some extra analysis. And so with this software new in the latest version that was just released in July, we actually added a little bit of functionality under this project to make that range azimuth grid able to be fully supported within MET. So if you remember that diagram I showed a few slides ago, we've basically made it so that all of the other tools can read in the range azimuth grid. So we have the ability to compute all of the different other statistics that are, point to grid, grid to grid, different types of verification. We can actually do that using the storm-centric output that comes out of the TCRMW tool. And there's also some automatic regridding that's available within MET Plus, and that now is supported through the range azimuth grid. And then finally, I don't have a bullet on this, but we have in the RMW analysis tool, we've added all of the filtering options since we have that track data. So you could go in and say, I want to filter off of specific type of storm or distance to landfall, that type of thing that is normally available within the TC tools. And so you can, put your verification together based off of that. All right, so that's where we are right now. Where we're going is towards a more unified verification framework. And so this is why we were advised to keep this a bit separate, because as we were looking through adding verification to all of these different application workflows, we started realizing that it was a little bit more of like a homegrown situation for each one rather than saying, well, verification is verification across all of these different applications. And so where we're going right now is merging the capabilities that are currently in the SRW app and the HAVS app into an independent application agnostic verification workflow. The benefit here is that any enhancement, like new verification metrics, data types, plots that are being developed in any other application could be then shared among the different other applications. Of course, different applications have different specific needs, and so those applications would have specific configurations that are designed for the needs of for instance, the TC forecasting community. And so we're looking at now bringing in the tools like GridStat, which is a grid-to-grid, PointStat, point-to-grid, series analysis that does compute statistics at each grid point throughout the domain, and then also bringing in some of the ensemble tools that have been getting used within the RFS benchmarking task. And so this basically is an easier lift by integrating that SRW app functionality and being able to use some of those tools for different applications. There's also more data ingest capabilities that are in the SRW app that we'll be able to bring in addition to the different OBs that are getting pulled for the HAVs. And so just some of the examples that I'm showing here up in the upper right is some large-scale verification that we've done that I think folks have seen if they're familiar with some of our work. This is using the series analysis tool. Below that is a scorecard. This is using the grid stat tool and computing a scorecard based off of QPF for different thresholds. And then on the bottom, I'm showing, these are actually plots from the RFS ensemble work. Okay, finish it up, yep. And so just to give an example of, we were actually planning to move into the direction of verifying the HAVS ensemble, and so bringing in, incorporating these tools that are already available with the RFS and then making them apply to the HAVS app. All right, so quick summary. Sorry, I ran through that pretty fast, but with 7 minutes trying to make sure I get it in time. So we have this HAVS verification framework right now established within the HAVS repository. It is sitting in a fork within the HAVS community repository, but instead of necessarily bringing it in to develop, we are planning on bringing it out and having it in this unified verification workflow. But we've been working on some initial capabilities that are focused on TC tools within MET+, and making some extra enhancements to those tools. And then looking forward, we're working towards this unified verification workflow where we can avoid redundancies across the different applications, but making sure that we still have TC-specific configurations in place. So with that, I can wrap up. Thanks.
Thank you.
Thank you very much. Just a statistic here, although we said 7, most people are finished in 9 minutes,
Okay.
9.5. So that's why we didn't really had chance. For some, could get a chance for question, for some not. So, but for this one, we may have one quick question. Please go ahead.
Yeah, great. Thanks for the talk. So most of your TC variables are focused on atmospheric and standard TC variables. Do you have any plans to include oceanic variables such as significant wave height as the track covers those?
That's a good question for this session. We don't right now, but I think that is actually, we should be moving in that direction. So yes, let's explore that for sure.
Thank you very much. So do you want to wrap up?
Yeah, sure. Okay. Thank you all so very much. We didn't even introduce ourselves. My name is Tracy Panara.
Saeed Mohimi.
We were both with the NOS together. Now I'm not. So thank you all for coming, and please reach out to us for any questions.
Yeah, and just want to add that there are 2 other people helping us to organize this meeting, and it was strictly asked to have a UFS coupling applications for this meeting. So if there is an abstract is not presented, it might be because of that kind of consensus. But thank you very much for great participation and submitting your abstract to this session. Thank you.
Tomorrow, Saeed's got another talk.
No, this is actually not me. Ufuk and Mansoor, they are going to talk about workflow development, more deep dive on UFS coastal workflow development, as well as more deep dive into the actual ocean models bringing to the UFS coastal. So there are 2 15-minute talk back to back. I will just moderate that session. Yeah, thank you.
Thank you all online.